Assalamualaikum and good morning. Today we enter chapter number 3. So for chapter number 1 and number 2, it is actually the revision from the undergraduates. And then I also explain about the tricks if you want to have that idea in your master level research and problem solution. So for chapter number 3, it is actually the tutorial is about the solution for Navier-Stokes equation. But before that, I would like to again introduce you the idea of Couette flow and Poiseuille flow. These two flow is actually discussed in our undergraduate for UTM student, but in very light level of discussion. Normally, in our undergraduate, we just show a few diagrams and then we will solve it in terms of real numbers. So means that now we will see in terms of the derivation form. Okay, we have two type of flow actually. One is Couette flow as shown in this slide, and another one is Poiseuille flow. I will explain that after this slide, after this session. Okay, so what is Couette flow? It is about surface resistance with uniform laminar flow. So in this section, we consider three two-dimensional laminar flows with parallel streamline. The flows are steady and uniform. That is, there is no change in velocity along a streamline. Using the momentum equation, we will first derive a general equation for the flow velocity and then apply it to three specific problems. So the problem is one, flow produced by moving plate. Number two is liquid flow down an inclined plane. And the third one is the flow between two stationary parallel plates, as shown in this slide. So first, as I write in here, so we need to derive the flow velocity first. So because this is to simplify the equation. So let's say we have some condition like this. We have an inclined plane. And then for sure, we know that the no-slip condition will occur at this point and the velocity distribution will form like this. Okay, so to draw the velocity distribution, you may draw like this one. So you have the increment of velocity, and until one point here, so the velocity will stay in uniform value. So it means that after this, the velocity is not increased. So that is the real nature when flow occurs. So and then to evaluate this one, so we draw a control volume. I think you already know about control volume. For example, we only discuss about this part. Okay. So and then we draw the free body diagram to explain about this part. So and then for sure, because let's say we have a liquid. So and then for sure the depth of the liquid will give us pressure, and then when the pressure acts on certain area, so it will create force. So here we could draw a force here pushing from left to right, and then I think you already know when we have control volume, we need to draw the pressure like this one. So means that it seems that these two pressure keep pushing on two sides to make sure that the shape of the control volume remain like that one. So so we have the pressure at this one is P times delta Y. So and then in this calculation, we know that force is equal pressure times area, but we only assume that we are two-dimensional. So we have the Z. Okay, I'm sorry. In this one, and we have this one is the Z, this the X, and this one is the Y. So means that here we are using delta Y times 1, means the width of this control volume is unity, mean it is equal to 1 unit. Okay, this is the to simplify our calculation. So you know that we have a pressure here and then another pressure occur at this one, and then here we write down as P plus dP ds at delta S here to show that. So in some textbook they will simplify the terms like this, so they only write P plus dP just to show that the pressure at this area might be same with the pressure at this one, or it has some modification, some changes, means delta P showing some changes. It may be positive, it may be negative. Okay, so and then this is the force that occur according to the pressure of the fluid. And then as we know that when fluid moving on the surface like this, okay, for sure it will stick, and then it's pushed at this side, so means that it will create a shear stress. Okay, normally when we have surface, so we will have shear stress. So that's why here at this surface, because the flow is same direction with the surface, so means that we assume that there is another force that will act on that surface, so we call it as a shear stress, a force from the shear stress. So I think previously in undergraduate you already know that force is actually tau times E. So the A here is actually the area of the shear stress, not the cross-sectional area. Okay, for pressure P times A equal to F. So the A here is actually the cross-sectional area. I mean the area which is perpendicular to the pressure. So here we could calculate as tau times A. So here the delta S here means the distance from here to here, and then again the width is unity, it's equal to 1. So means that we remain the area is delta S times 1. So we just write as delta S. So here we write that d delta tau over dy delta y. So in some text, it's okay for you to just imagine that it is just tau plus d tau, means plus d tau like this one, means that we have a shear stress here. So and then we have another shear stress here with some changes. It may be negative, it may be negative, it may be equal to 0. So means it may be carrying the same value of shear stress. So and then the last one that we need to write in our free body diagram here is the weight. So we know weight here is occur because the gravity pull the element. However, because we want to evaluate these forces according to the axis, so we split into these two elements. So we have this Z element, and then we have this one. Okay, so I think, oh no, this one. Okay, mean the perpendicular axis here. Okay, so I think if we write the component value of weight, so we could write as W sine theta because the inclination here is theta. So this is the explanation for this diagram. Okay, so and then again, so in this in this diagram, I will show you how to solve by using the balance of forces. But at the end, I will also show you how to use the Navier-Stokes equation to solve this problem. So let's say in equilibrium, or in equilibrium, so the total force is equal to 0. So means that the total force here is equal to 0, means that we need to sum all the forces. So the net forces here can be written as this one. This is the inlet, and then this is the outlet. So if we solve this one, so we have negative dP ds delta S delta Y. So and then the net forces due to shear stress can be written as this one. So and then we have the d tau dy delta y delta S. Okay, so normally for pressure here, okay, we will take the negative one, and for the shear stress, we will take the positive one. So it means that, okay, so if we have shear stress here and also shear stress here, so we only take only the different value of the shear stress. So, but however, in pressure, we, according to the experimental work, we found that the pressure will going to decrease, because as we know, if we have a pipe, normally we will talk about the pressure drop. So means that the common phenomenon is the pressure is decreased. So we because it decreasing, so we give them the symbol of the minus symbol here. So and then the gravitational force, so we take the component W sine theta, so and then we change the W here with the mg, so I think you already know, and then we substitute the m here with the rho and volume. So I hope you know about this one. So and then we substitute the volume here by looking at the diagram, and it can be reduced as delta y time delta s times delta y. So if we see the diagram here, so this is the delta s. So and then this is the delta y, and then the width here is equal to 1. So it's still that we could calculate the volume is delta s times delta y and times 1. So that's why we only substitute delta s and delta y only. Okay, so and then, so we have a sine theta here. So the sine theta here, you know, previously in our chapter 1, we learned about the Cartesian coordinate, we have the polar coordinate. So if we remain the symbol of sine theta, so mean maybe we need to calculate in terms of polar coordinate. Just to make it to ease the calculation, so we replace the sine theta here by looking this diagram. So let's say we have this is the theta and this is the length, and the dz here is the height of this one. So means that we could say that the sine theta from that symbol can be replaced by the negative dz over dy. So the dz here is, we put a negative sign because we found that the motion is actually going downward. So downward is the negative side of Cartesian coordinate. So we substitute everything. So we will have this one, the gravitational force. So and then, so we put everything, all forces is equilibrium, it's balanced. So and then we could have, so how to put the force is actually we could see from this one. So we have the force here, okay, and then we have the sine here, and then we have the shear stress here, okay. So and then, so we could have the d tau dy, okay. So and then we divide it as delta s delta y. So finally we could get this one, the value of d tau dy. So here we substitute the value of the shear stress here. So with the idea of Newton shear stress law, so it is equal to mu du dy. So that's why we substitute in this one, and then we could get this idea. Okay, so mean we have so we put this equation as equation number 1. So and then we will use this equation to solve that 3 situation. Okay, first we have this situation, which is the flow produced by moving plate. So the idea is, if we have 2 plates like this one, we always assume that the bottom plate here is the fixed one. So and then the top bottom here will pull by certain velocity. And then because we assume that the no slip condition occur at both walls here, so mean at fixed wall here the velocity is equal to 0, but at this moving wall, this molecule is stick on the wall and relatively it will move at certain velocity because the plate is moving at certain velocity, so means that the molecule which is stick on the surface also relatively move at a certain velocity. Okay, so and then we put this diagram in horizontal like this one, and then we could assume that there are no dpds in here. So dpds means there are no pressure gradient in this situation. So and then we assume the dz ds is equal to 0. So this is the assumption for this one. And then if we substitute into the equation number 1 here, so we found that it is equal to d square u over dy square equal to 0. So I think this situation also discussed in Navier-Stokes equation in previous chapter. Okay, so this is actually the idea. If we only think about the forces that occur that act on the control volume. So I think from here you already know what to do. So we need to integrate 2 times. So okay, so I show you again. So if you want to use the Navier-Stokes equation, so this is the common Navier-Stokes equation. So because we are discussing only 2-dimensional, okay, only x and y, so and then we assume that there are no velocity of v and w, so means there are no v and no w here. So and then it is steady state, so mean that the velocity is remain constant, mean there are no changes with time. So we have du dt is equal to 0, so we have d 0. So and then it is a fully developed flow, so mean du dx is equal to 0. So we have all of this is equal to 0. Z is not okay. So here what I hope you could still understand the meaning of du dx. So means there are no changes of velocity along the x direction, and this one is there are no velocity along the z direction. So sometimes in wide channel, if the width is too long, is too wide, we could assume this assumption. So the idea is if the width is too long like this one, so this is the 3D. So and then let's say the width is here, and then for sure the no slip condition will occur, but it start only the no slip condition will occur here, and then it will slope here, but all the velocity profile will remain constant, and then at just one short path here, the velocity is decreasing and back to 0. So because this area is very small, so we assume that this is might be 99% of the condition. So that's why we call that the velocity of u here, so each is actually not changes along the z-axis. Okay, so I hope you could just understand what is the meaning of du dx, du dy, and du dz. Normally, if you want to have your Navier-Stokes in your simulation later on, so you need to think about this. You need to understand the meaning of each parameter. So that will make your simplification easier. So we have, and then the gravity will not act on x-axis, and then there are no pressure gradient. So finally, we also get the idea of d square u over dy square equal to 0. So and then I hope you could do this. So we substitute with the boundary condition. So the boundary condition is actually what happened in the situation. So here we have 2 points, which is the boundary condition, which is the bottom plate and also the top plate here. So and then we describe about the velocity. So here the velocity is 0. So at y equal to 0, but here the velocity is equal to capital U, and the location is y is equal to L or y equal to h or something like that. The distance of this one. So means that here we say that, okay, we have 2 conditions. u equal to 0 at y equal to 0 and u equal to capital U at y equal capital L. So and then if we integrate this term twice, okay, so and then we could get this term. We have two constant C1 and C2. So and then if we solve these two, we substitute these two boundary condition into this equation. So finally, the simple one is the C2 is equal to 0, and then we could find the value of C2 is equal to 0, and then we could find the value of C1, and then finally we could have the equation for the velocity profile is U is equal capital U y over L. Okay, so and then here if you want to substitute the idea of Newton law of viscosity, so mean tau is equal mu du dy. So sometimes people will change with mu u over L, because the u here, if there are no changes of u, it is okay for us to substitute the value of velocity u. And then the y here means the gap between the two plates. So maybe we could replace with the value of L. So this idea is actually introduced by one French scientist named Couette. So we call this is for the Couette flow. So and then extend from this idea. Okay, so we look for example here. If the fluid between the plate is SAE 30, lubricating oil at T equal 38 degrees Celsius, the plates are placed 0.3 millimeter apart. The upper plate is moved at velocity 1 meter per second. So what is the surface resistance for 1 meter square of the upper plate? So mean the surface resistance means the resistance, the force that we need to we need to push the plate to make sure it move at 1 meter per second. So the idea is very simple. So we calculate the shear stress. So it is the simple calculation is mu du dy is equal mu u over L. We substitute everything, so we could assume that we need force around 333 newtons to push that upper plate to make sure it could move at velocity 1 meter per second constantly.